In our paper, we propose a framework for output prediction of nonlinear dynamical system inspired from the Kazantzis-Cravaris-Leuenberger observer. Our work focuses on autonomous and nonlinear dynamical systems defined by smooth vector field f and h. We also assume backward and forward completeness, which means that any trajectory x of x0 and t are defined for all time. Yet, we do not assume observability properties. This system produces observations that may not contain enough information to reconstruct the initial state variable x. The output prediction problem aims at forecasting the future value of an observation given a small sample of the beginning of y. This task can be difficult since we do not have access to the generating system f and h, which can be of arbitrary complexity. Note that one may not solve this problem for all possible observations, but at least on a smaller subset. We propose a general framework to solve the output prediction problem by defining another latent dynamical system. We denote as d the latent state variable and g its dynamics. The evolution of z depends on the observations. To be an output predictor, the green system must satisfy two properties. It must be a uniform exponential contraction and a generating model. The contraction property is interesting for this application. A contracting model forgets its initial condition. Thus, for a given observation, the latent state converges to the same trajectory regardless of the initial condition. The second property postulates the existence of a mapping function psi from the latent state space to the observation space. Thus, one can rewrite the green system in an open-loop manner that does not depend on the observation. Theoretically, a generating model could be used directly for output prediction by rolling out the latent dynamical system. The resulting trajectory will then be fed as input to psi to obtain the observation. Yet, this requires perfect knowledge of the exact initial condition z0, which is not available. Practically, let us have a look on how such output predictors should be used for solving the output prediction problem. For now, we assume perfect knowledge of g and psi. Here is an observation y from the original dynamical system. We could predict y by rolling out the latent open-loop model. The problem here is that we do not have access to the ground truth initial value z0. To overcome the issue, we leverage the known part of the observation and the contraction property. We roll out the latent dynamical system in a closed loop with the ground truth observation during the first known time steps, such that the trajectory of the latent state z converges to the true trajectory starting from z0. During the forecasting step, we exploit the generating model property to open the loop and forecast the observation using the mapping function psi. The prediction pipeline is summarized in this figure. Starting from a random initial condition, the latent dynamical model leverages the known part of the observation and the contraction property to convert to the correct latent trajectory. The rest of the observation is forecasted using the generating model property and the mapping psi. We can compute the following bound on the forecasting error of the observation. Without going into details, the error bound increases with prediction horizon p and decreases with the number of known time steps. We derive the Kazantzis-Cravaris-Leuenberger observer structure to build our output predictor. We consider the case in which the contracting model is defined with an Hurwitz matrix A and a vector B, so that the pair AB defines a controllable system. The stability of A guarantees that our KKL-inspired latent model defines a uniform exponential contraction. One can also prove that there exists a mapping psi such that the model also defines a generating model. To be precise, if the dimension of the latent state z is superior to 2 times the dimension of x plus 2, the ensemble of A matrices such that psi does not exist is of 0 Lebesgue measure. This means that the choice of A can be arbitrary as long as it stays an Hurwitz matrix. Thus, if our latent KKL-inspired model defines a contraction and a generating model, it is a suitable choice for our output prediction pipeline. Nonetheless, finding a usable form for psi is not trivial and requires complex calculus in most cases. Instead, we model psi as a multilayer perceptron and learn the function using a small and finite subset of observation. In this formula, sigma represents an activation function, We denote as theta the set of trainable parameters of the MLP, that is W1 to WN and B1 to Bn. We optimize theta through gradient descent, minimizing the following cost function on a small set of observations YD. Note that we also learned the matrix A from the latent dynamical system. Our experiments have shown that this improved the overall performances while maintaining the average property of the matrix. Our proposition is arguably related to the Koopman operator theory, which leveraged the existence of a latent space of infinite dimension where the dynamics of the system is linear. Yet, there is 4 key differences with deep KKL. Firstly, since the Koopman operator is by definition of infinite dimension, practical implementations are limited by an approximation of the operator. Deep KKL guarantees the existence of a solution in a finite dimension space. Secondly, the latent space created by the Koopman operator contains information about the full state, while our proposition requires only the observable part of the state to be embedded. Thus, our contribution does not require neither a measurement of the complete state nor the observability of the system. Thirdly, Koopman requires the mapping from the state to the latent representation and its inverse, whereas deep KKL only requires the identification of the inverse mapping, that is, from the latent space Z to the observation Y. Finally, methods based on Koopman operator do not take benefit from access to the first step of the observed trajectory. Their predictions are solely based on the initial state of the system. Now that we have presented our output predictor, we can look at how it performs on different chaotic dynamical systems and against 2 classic deep learning architecture close to deep KKL. We evaluate output prediction performances on 4 systems: a van der Pol oscillator, the Lotka-Volterra predation model, the classical Lorentz attractor, and a mean field model for a fluid past a cylinder. We choose 2 classical deep learning architecture to compare with deep KKL, a recurrent neural network and a gated recurrent unit. You can see these baseline models as a replacement for a KKL-inspired latent dynamical model in our pipeline. This figure shows the evolution of an observation starting from a random initial condition for each system. The black line represents the ground truth value of Y. Note that this particular observation has not been seen during training. The vertical dashed black line delimits the closed loop step, during which we provide the Y to the model, from the open loop step, that is the prediction phase. The blue and green lines are the prediction made by the 2 baselines, RNN and JRU. Interestingly, both baselines take advantages of the closed loop phase. Nonetheless, proving that the gated recurrent unit defines an exponential uniform contraction remains an open question. RNN and JRU fail to accurately track the ground truth observation during the prediction step. The red line corresponds to the prediction made by our deep KKL output predictor. The model rapidly converges to the ground truth observation during the contraction step and accurately tracks the future value of Y for a long period of time. The visual results are confirmed numerically. On one hand, using deep learning allows to readily and rapidly compute the mapping function psi for a wide range of systems. On the other hand, it may suffer from generalization issues. In this graph, we evaluate the output prediction error as a function of the initial condition for van der Pol oscillator and Lotka-Volterra predation equations. The x and y-axis represents the initial condition used to generate an observation with each system. The black pixels indicate initial conditions used to generate the training data. The square delimits the sampling domain. Initial conditions outside of the square can be referred as out-of-distribution trajectories. We evaluate the prediction error of deep KKL for each observation generated from each initial conditions on this figure. Red pixels indicates accurate forecasting, while blue pixel indicates less precise results. Deep KKL generalizes well to in-distribution observation, which here are inside the black square. Initial conditions that are far from the sampling domains may impact the performances. Actually, the prediction error is related to the vector field of each dynamical system. Deep KKL generalizes well for observations that are not too far from the one in the training dataset. Another source of error concerns the fact that the learned function psi is actually an approximation of the true mapping. The universal approximation theorem demonstrates that for a neural network of arbitrary y's, there exists a set of weights such that the error between the true mapping function and our neural network approximation remains bounded by a given constant delta. This modifies the upper bound on the prediction error. In addition to the term due to the approximation on the initial condition, another term appears due to the approximation of psi. The error delta is hard to evaluate and strongly depends on the training data. Future work will consist on trying to find a better upper bound for the neural network error that take into account the composition of the training dataset, probably using modern mathematical tools such as back learning. Thank you for your attention, and if you have any questions, I will try to answer it as best as I can.